Hello, my name is Blas. In this video I will show you how to simulate a steady-state heat transfer problem using Git and the problem type siphon to the heat. For that, I will replicate this example that I found on the website sciofdoom.com. The example is about a wall made out of PVC with two boundary conditions. At one side of the wall we have a fixed temperature of 50 Celsius degrees, and at the other side of the wall of 10 Celsius degrees. We also know that the wall has 2 meter width, and of course the conductivity coefficient of the material. We need to calculate the heat flux that travels through the wall. The analytic solution gives us 3.8 watt per square meter. Let's start drawing a simple geometry. I will say the problem unit. Now the material. We can see that the K coefficient matches the one in the problem. We need to set the boundary conditions. 50 Celsius degrees at one side of the wall, and 10 Celsius degrees at the other side of the wall. We generate a mesh. Simple mesh will be enough. You can see that we have 9 nodes and 8 elements. Let's calculate. Here is the temperature distribution that we get. At one side of the wall, we can see it's 50 Celsius degrees, and at the other side of the wall is 10 Celsius degrees. But what we want to know is the flux going through the wall. We can see here that the flux is constant through all the wall, and we get 3.8 watt per square meter. Exactly the same result that the analytic solution. We can also draw the vectors. We can see here that the flux go from the left to the right. We can corroborate this solution. For that, we will replace one of the boundary conditions for the flux that we get. I will remove the boundary condition at the right side of the wall. So, instead of having a fixed temperature of 10 Celsius degrees, we will have now a flux going out, and for that the minus sign, of 3.8 watt per square meter. The problem changed. What we don't know now is the temperature at the right side of the wall, and that is what we want to calculate. If the magnitude and direction of the flux that we set as boundary condition are the correct one, then the temperature that we will get at the right side of the wall should match with the one that we use as boundary condition in the first simulation. And here we go. The temperature at the right side of the wall is exactly the same that we use as boundary condition in the first simulation. and in this way, we corroborate that the flux is the correct one. Thanks for watching, I'm Blas, and I hope to see you in the future videos.